We're going to move into the session now on research. So we've got three speakers now in this session. So I would like to kick us off by introducing our first speaker, who is Anthony Darby. So Anthony is Professor of Structural Performance and Design at the University of Bath in the Department of Architecture and Civil Engineering, with over 25 years experience in the use of advanced composites in construction, particularly the strengthening of concrete structures. He's led the second and third editions of the Concrete Society's TR55, which is the UK's key design guidance for strengthening concrete using fibre composite materials. And he served as the UK principal expert on Eurocode 2 for the input on reinforcing and strengthening concrete with fibre reinforced polymers. And Anthony's going to be presenting today on ensuring ductility in FRP strengthened concrete structures. So Anthony, over to you.
Okay, thanks very much for inviting me today. So yeah, I'm going to talk a little bit about some of the research we've done that's fed into some of these design guidelines and Annex J of the Eurocode, and specifically focusing on ensuring ductility in FRP concrete strengthened structures. So we normally get ductility from concrete structures by allowing the steel to yield. So steel is obviously an elastic plastic material, but carbon fibre reinforced polymers, FRPs, are generally elastic, brittle materials. So can we actually get a nice ductile response from a strengthened structure? Now, the FRP either fails by tensile rupture, which happens particularly in strengthening columns, but probably that's about it, generally speaking. But the more common failure mode is debonding of the FRP from the surface of the concrete or pulling off the concrete cover. So both of which are sort of very brittle modes of failure. So how do we generate ductility in an FRP strengthened structure? Well, first of all, we can ensure that we get mobilized sufficient ductility from the reinforcing steel itself that's already inside the concrete. Secondly, we can try and increase the ductility of the concrete by confining it, which is basically what we do with column strengthening. Or thirdly, we can get a sort of pseudo ductile debonding failure mode for FRP if we use it in the right way. So I'm just going to go through some of the research aimed at understanding the sort of ductility of structures strengthened with FRP, starting off with flexural strengthening. So flexural strengthening, we attach carbon fibre plate or sheet to the soffit of a beam on the tension side of the beam or slab that we want to strengthen to act as external tension reinforcement. So if you've got a beam that's been designed to resist the ultimate moments, if we want to increase the capacity of that beam, then obviously the bending moment is going to increase, and we therefore need additional strengthening over the region that exceeds the original moment capacity to help resist those additional loads. We can analyze them using standard sectional analysis. So we've got our compression forces in the top of the beam that are in equilibrium with our tension forces in the bottom of the beam from our steel. So if we add FRP, then we're going to get an additional tension force. And that's obviously got to be balanced by some extra force in the compression zone. And we can only really get that by increasing the depth of the neutral axis and increasing the amount of concrete that's in compression. And when we do that, you'll note that the strain in the steel here decreases. And so we're going to start reducing the amount of ductility that we can achieve in the section. So more interestingly, what happens when we've got statically indeterminate beam? So this is a continuous beam. We've got a load, it's been designed, maybe with redistribution in mind right from the start, but it's reached its full capacity. And if we want to strengthen it, there are different options that we can do. So our first reaction might be to strengthen both the hogging and sagging zones by adding FRP on the tension side. And that will obviously increase the hogging and sagging moment capacities. Or we can just increase the sagging moment capacity. So we get increase in moments like that, or we can increase the hogging moment capacity. So we get a moment diagram that looks like that. Now, the problem is when we design reinforced concrete beams, continuous beams, we rely pretty much always on the lower bound theorem of plasticity. We don't really know what the bending moments are in the beam. If the central support settles slightly, then our bending moment diagrams go look like that. If the end supports settle, then we end up with a bending moment diagram that looks like that. So lower bound theorem of plasticity allows us to get away with that because the moments will redistribute into the moments that we've designed for. But can we do that when we've got an FRP strengthened structure? That's the question we sort of were asking ourselves. And the problem is when we start adding FRP, our moment curvature relationships are no longer a nice ductile relationship. The more FRP you put on, the less ductile it becomes. And so Annex J actually states that unless a more rigorous analysis is undertaken, members strengthened with adhesively bonded reinforcement should not be analysed using linear elastic analysis with redistribution or plastic analysis. So it sort of specifically prohibits it unless more rigorous analysis is undertaken. So can we actually achieve moment redistribution? So we did a whole load of tests on continuous beams with a load on one span, and we designed these specimens. We had several specimens, some slabs, some T-beams, but we designed them to redistribute from the sagging region into the hogging region. And if we were successful with that, we'd end up with a sort of moment diagram that looks like that, where we can get extra moments into the hogging region away from the sagging region. So this is our control specimen with no strengthening on it. So the red is the elastic distribution, and the black line there is the redistributed moments that we measured. So we got 34% moment redistribution there. But as soon as we add FRP in that sagging region that we're trying to redistribute from, then we're getting hardly any redistribution, only 6.5%. If we strengthen both the hogging and the sagging zones, then again we get very little moment redistribution. But if we only strengthen the hogging region and leave the sagging region unstrengthened, then we can redistribute massive amounts of moment from the sagging region into the hogging region, even more than the original control specimen. So only modest redistribution is possible out of a strengthened zone, but we can get very high amounts of redistribution from an unstrengthened zone into a strengthened zone. And then the failure of these beams was ultimately by that debonding failure. So we asked ourselves, well, if we could prevent that debonding or delay that debonding, can we get extra redistribution? And we did. We anchored our FRP tension reinforcement by using these sort of angled U-wrap anchorages. There's different ways you can do it, but this is what we chose. And when we apply that U-wrap anchorage in that sagging zone, we can get extra tension into that and strain into that FRP, and therefore also into the steel. So we can get a bit more redistribution of moment. Same thing if we strengthen both the hogging and sagging zones. But really, just strengthening the region that you want to redistribute into is the best approach. And then, as Annex J said, unless more rigorous analysis undertaken, you can't redistribute. So what we wanted to do was work out how we can do that analysis. So we took our beam, we separated it into a whole load of different cross sections, and at each cross section we had a moment curvature relationship. So unstrengthened section, sagging region, hogging region. We started off with an elastic moment distribution. Then we calculated for the moments at each location what the curvature was. And then we created an effective stiffness at each location. So the red sort of represents the variation in stiffness along the length of the beam. And then with that new stiffness distribution, we calculated a revised moment distribution, and we kept going until we got sort of convergence. So that bending stiffness sort of varies as we sort of continue to increase that load. And so we end up with a moment distribution that reflects the actual behavior of the beam, taking into account those moment curvature relationships. And this is a comparison of experimental data and our analytical model showing how well our model fits that data. So that's an approach that we could use. Okay, let's just quickly move on to shear strengthening. Shear strengthening is done by, again, applying carbon fiber as sort of external stirrups, usually in a sort of UWRAP configuration on the downstand of a beam. So there's our FRP. So you can see that it doesn't really extend into the compression zone, but as best we can do, unless we sort of have some sort of anchor. And when a shear crack forms, we get a contribution from the steel, and we get a contribution from the FRP, and that FRP contribution is, again, normally governed by the bond resistance of the FRP. And so it is assumed that we can get both of those happening at the same time. And we wanted to explore that for some large-scale beams. Most of the beams that have been tested have been little sort of small-scale beams, that sort of size. So we produced beams that were up to 720 millimeters deep. So those are the beams in our lab. You can see the strengthening that we've applied to those beams. And we applied some different strengthening techniques. So surface mounted UWRAP, both heavily and lightly strengthened. Surface mounted UWRAP with this sort of anchor where we cut a slot, pushed the FRP into that slot and bonded a bar in there to try and anchor the tops of that FRP. And then we also looked at this deep embedment strengthening method that we developed at Bath. And that involves drilling holes right through the section, injecting adhesive into those holes and pushing a bar, reinforcing bar, so in this case carbon fiber bars, but it could be a steel bar, into those slots and bonding them in. So they're inside the concrete. So we had, how do I make this work? All right. So this is the UWRAP specimen. So that sort of crack along the top there is where it started, the FRP started to debond. And then we get that sort of full shear failure. And you can see as the test progresses, how that FRP has debonded from the surface of the concrete. This is what it looks like underneath when we pull off that FRP. And you can see that actually the effective width of that FRP is actually pretty small when we consider the full shear span of that beam. So the FRP here is not going to be very effective, and it's certainly not going to be in that flange zone. This is the beam with anchorage at the top of the FRP, and again we sort of fairly quickly see it sort of start to debond. and eventually the anchors sort of pull out at the top there. And there you can see that debonding happening again. So initially that debonding happens in the middle of the FRP, where the shear crack forms and then propagates towards the edge. And then this is our beam with our deep embedment strengthening. And the advantage of the deep embedment strengthening is that it is the full depth of the beam. So you can't see it because it's all internal, but it will therefore strengthen the full shear span and be effective over the full shear span. And as it fails, it debonds, and it debonds gradually because it's confined within that concrete. Okay, now these are the results of the test, and unexpectedly, we basically got no increase in strength. So this sort of grey line here is our unstrengthened specimen, and the dark blue and the black are our strengthened specimen. So we're getting hardly any increase in capacity. In fact, we weren't getting an increase in capacity. And also we can see that the steel yields basically at the same time that the FRP debonds. So we're not necessarily getting the contributions combining together. If we anchor the FRP, we get a little bit of extra capacity compared to our unstrengthened specimen. But again, the debonding and the steel yielding happens pretty much at the same time. With our deep embedment bars, we get a bit more of a strengthening happening. So this is where the steel yields. So we're getting extra capacity beyond that, and we're getting an increase in capacity. So the deep embedment strengthening, 28% increase in capacity. The anchored ones, 8% increase in capacity, but the ones with no anchorage, no increase in capacity. So strengthening can, in certain instances, result in no actual increase in strength. Anchoring the FRP can improve that capacity by delaying that debonding, and deep embedment seems to work very well in terms of increasing the strength and providing a more ductile failure. Okay, last thing I just want to touch on is column strengthening and confinement of columns. So we strengthen columns by wrapping them with FRP transversely, so that when we load it, the column expands and the FRP confines that concrete. So we get an increase in our stress strain response, unlike normal unconfined concrete. Now with circular columns, that's very effective. So for concentric loading, we get nice uniform confinement all the way around the section. For rectangular columns, though, we only really get that confinement occurring at the corners, and most of that confinement is just literally at those corners. And that confinement is the amount of confinement that we can achieve is related to the stiffness of the FRP confinement and the strength of the FRP, because ultimately they do fail in rupture. So what we want to do is look at some large scale testing. So again, so 99% of all testing is on these little small scale columns, where we looked at very large scale columns. So we did these at the BRE, which had the biggest compression testing machine in the country. And we tested them under concentric loading and 2 levels of eccentric loading. And what we found was that under concentric loading, we got a nice sort of failure where ultimately it's failed by rupture of the FRP. But when we had eccentric loading, we got debonding along the side faces. So all these red crosses represent where the FRP has debonded. And that has an influence on the stress strain behavior. So that pink is what we actually found, and all the models tell you that it's going to be something like that. And we get this sort of reduction in confinement due to that loss of stiffness as the FRP debonds along the sides of square and rectangular columns. So actually we're only getting that sort of increase in strength rather than what we might anticipate. And that's due to the fact that if we've got some concrete in tension and some concrete in compression, the tension side, we're getting no mobilization of the FRP. We get this sort of linear increase in the strain in the FRP along the side faces. And so we're getting shear stresses along that side faces that if we exceed the shear strength of the concrete, then we get debonding happening. And that's what results in that loss of stiffness of the FRP, because we rely on bonds to achieve that stiffness. So Annex J sort of has a limit on the amount of eccentricity that you can strengthen a column with to prevent that sort of thing from happening and us getting very little increase in capacity. So how do we ensure ductile response? So in general, ensuring yielding of that existing reinforcement, anchoring the FRP can help increase the strains in the steel and the FRP to allow that to happen. In flexure in particular, for statically indeterminate structures, we need to arrange our FRP reinforcement to allow redistribution out of unstrengthened regions into a strengthened region. For shear, consider deep embedment technique for enhanced shear ductility, because yielding of steel might promote debonding or vice versa, and prevent that simultaneous full contribution from the steel and the FRP. And then for column confinement, avoid strengthening square and rectangular columns with large moments or large eccentricities of load. And similarly, with those columns with large aspect ratios, you get a sort of similar effect where it's not very efficient. So I need to thank all my collaborators and PhD students and the technical support that we've had on all of that testing. But thank you very much.
Okay, so our next speaker is Emily Bowyer. Emily is a PhD student at the University of Bath, researching structural adaptations for building reuse. Her work aims to support more sustainable design practices by developing a systematic method to assess whole building reuse potential at early design stages. So Emily's going to be presenting today on defining a suite of structural adaptation options for existing structures. So Emily, over to you.
Hi, thank you for having me here today to speak. As you've heard, I'm currently researching a PhD at the University of Bath, and I've currently got about 1 year left. And today, I'm talking about defining structural adaptation options for adaptive building reuse. First of all, I suppose, as many of you will know, there's obviously a lot of focus on, for example, climate emergency and reducing embodied carbon in the construction industry. The construction industry accounts for about 1/3 of global emissions. We use about 1/3 of the world's resources. And in the EU specifically, about 1/3 of the total waste is from construction and demolition. So it's just give an idea of how much impact we can actually have if we can make a positive change. Right, this graph on the right, I'm sure lots of you will be familiar with. It's the UK GBC graph about the carbon reduction potential as time goes on for a project. For me personally, I was in practice and was sort of, working around optimizing things and working in this sort of build clever sort of section. And now I've gone back into academia to do my PhD, where I am focusing on this sort of potentially more carbon reduction potential section of build less and trying to use our existing assets. And that is via building adaptation, which, as you can see here, generally accepted to be any work to a building over and above maintenance to change its capacity, function, or performance. There's been increasing information about this in the news as well as within research and practice. It really aligns with circular economy, which is generally understood to be about maintaining the highest value form of our materials, in this case, the actual buildings. The aim of my whole PhD is to enable more building reuse, and that's through the articulation of what opportunities and options there are for structural adaptation. Just to give a quick overview, I'm trying to suggest a framework which is sort of simplified here in this diagram. I'm trying to take candidate buildings. So by that, I mean the existing buildings we already have, and then briefs, client briefs for what we actually want or requirements, which is the aspirational buildings, and then combine those with the structural adaptation options using a computational model so that I can then evaluate these possible solutions to investigate the equivalent CO2 cost, the level of those interventions, those structural adaptations, and also hopefully get some insights into the suitability of different buildings to different briefs. This was quite a lot. We quickly decided that a phased approach was needed, and the thing I'm going to be talking to you today is just these structural adaptation options here. Cool. Okay, again, we had to break this down somewhat, and first task was to come up with a list of structural adaptation options. And for this study, I was considering these three main building typologies: concrete frame, load-bearing masonry, and steel frame buildings. Next was to think about the considerations an engineer might be thinking about when selecting different structural adaptation options. And the four that we ended up focusing on were complexity, time on site, project risks, and functional difficulty, which I will go into a little bit more detail in a minute. The process for this particular study was using expert elicitation to develop and use a rating system so that we could analyze how important these different considerations were for the different structural adaptations. Then, of course, the fun bit, interrogating the results, making lots of graphs. Okay, for anyone that hasn't come across it before, expert elicitation is a formal process that you can use to get specialized knowledge or specialized judgment from experts in the field, and it's particularly helpful for questions that either have limited empirical data or are really hard to quantify. For me, for this study, on the right here, again, a simplified diagram, we had a phase 1 survey that was done virtually. We then had a virtual feedback and discussion workshop with all the participants together before then having a secondary survey again. So that's a quick overview. For this, we had 16 participants who were able to complete all 3 stages fully, which is a really important part of the methodology. And you can see on the right that the experience of the participants generally was between 11 and 30 years of working as a structural engineer. 75% of the participants had worked on more than 10 adaptive building reuse projects, and the range went from 3 to 320. So as you can see, a lot of variation there. In terms of the buildings that the participants had worked on, you can see here that the largest number was medium scale, which we had defined as multiple dwellings, mid-rise, so it could be mixed use. When I'm talking about the buildings here, I mean the existing buildings, so those candidate buildings before those adaptations had taken place. 88% of the participants had worked on at least one of each of the 3 different building typologies, which is helpful for us. And you can also see here a relatively high number of load-bearing masonry building typologies. This is something we discussed in the workshop, and we generally attributed it to the prevalence of that building type here in the UK, as this was UK focused, and also the age of them lending the load-bearing masonry buildings to come up quite often for adaptive building reuse. Okay, on to some of our results. The first thing that I asked participants was about generalized barriers to adaptive building reuse, and they had to rate how often a barrier came up in the adaptive building reuse projects they had worked on, and also how severe that was, and as you can see, from 1 to 5. Here we've got our severity on the x-axis, frequency on the y, and you can see that this first group up here, budget, construction time, and risk, all 3 of those came in quite high for severity and frequency, and all have really clear links to cost and financial aspects. It was good to see at the other end, low occurrence and low severity was the concerns about lack of skills or experience in a design team, and similarly with a lack of precedent. So hopefully that can only be good news for adaptive building reuse. One thing to note here as well is the severity of client motivation and understanding. These comments here are just a couple that I took out of what came back for the responses. There was quite a theme that actually many of our experts had experienced a real mismatch between the client brief or what the client wanted and the potential of the existing building they had. So that's just something to be aware of going forwards. Okay, we then turn to focus on the actual considerations that we're going to look at these adaptation options with. And so the participants rated again how important this whole list of considerations were when they were selecting a structural adaptation option. At the top, we can see fire and risk in health and safety, both clearly linked to existing regulations, and not surprising given the recent industry focus on fire regulations. The next three down are all, once more, fairly clearly linked to cost. Cost here, by the way, is in terms of capital cost. And although the other categories weren't not important, they would clearly yield to those first higher ranked considerations. Some of these considerations existed before the first survey. Some of them were put in as a result of the workshop. For example, the building remaining operational. That was discussed quite a lot in the workshop because it was identified as a good factor to increase project viability. For example, client could keep an income stream going if the building could be operational. I couldn't ask all of my participants to rank every structural adaptation against each of these, so the considerations were compiled into 4 overarching ones that they would be asked about. So these were the complexity, the time on site, and the project risks, and then finally this functional difficulty. So this was one of the considerations discussed quite a lot in the workshop, which is sort of where it was formulated. And it is about considering the compromise or coordination with other disciplines, how practical it was in the building, and then also an aspect of future flexibility. Okay, we're now going to go into the results. Don't panic. I know there's a lot going on this slide. I'll just talk you through the format, so it'll be the same for the next 4 slides. So if you can see the laser pointer, down here on the left, we've got the different structural adaptation options. And then each of these 4 columns relates one each to those 4 considerations I discussed. And each one has got a rating of 1 on the left, which correlates to it being least challenging, to 5 on the right-hand side, which is extremely challenging. The histograms give us the distribution of the results, the responses from the experts, and the green lines give you the mean values for each one. Don't worry too much about the actual numbers. The idea of this is that we've got a visual comparison, so I can sort of talk you through some of the highlights. And then finally, building typologies. Orange is our load-bearing masonry, turquoise is the steel frame, yellow is the concrete frame, and then the grey ones is where we left all 3 grouped, as we felt we didn't need to distinguish between the typologies. Right. This slide is all talking about the removal type structural adaptation options. So that's where the main point is to take out elements or members from the structure. As you can see at the top, with partial floor removal and whole floor removal, in general, the whole floor removal was rated as more challenging or potentially more problematic by our participants to perform than partial floor removal. It's also, you can see, especially for complexity and time on site, that that for concrete typologies, there was an increased challenge that you can see here. You can also see from this that within this structural adaptation type, the lateral stability elements, probably not surprisingly, came out as some of the most challenging. And the removal of non-structural screed seemed to be at least the simplest for complexity, but generally rated fairly low, i.e. less challenging for the other aspects as well. Okay, moving on to our strengthening type structural adaptations. Again, you can see up here at the top that although it's not by a lot, but again, our concrete framed structures seem to have a slight increase in complexity, though not a lot of difference in terms of the functional difficulty. This middle section here, which includes our post-tensioning, which was clearly seen as the more challenging of these adaptations, also includes our FRP wraps, FRP strips, and overlays. Those are all grouped together as, in general, they came out as more challenging, and from commentary in the workshop and the survey, this was generally due to them being viewed as more specialised. So that's strengthening. Our foundation types, we left them all non-distinguished, so all is grouped together, as the foundations were deemed to have less of an impact on the superstructure. And you can see for example, the functional difficulty is more or less the same for all of them. But we can also see that mini piles or screw piles was deemed the least challenging of these options in order to adapt your foundations. Okay, our last category of structural adaptation type is the additional. So this is where we're adding elements. And again, you can see consistently for these top three, where we distinguished each of the three typologies, that the concrete framed construction seems to be presenting more challenges, or at least was rated as such. Though realistically, there's not a lot of difference between the load-bearing masonry and the steel for each sort. Similar story for adding our cross bracing for all of them, but the functional difficulty, there's quite a significant increase in the perceived challenge or difficulty of implementing an adaptation. For this group, our adding or increasing of the cores, which again wasn't specified for typology, was seen as the most challenging adaptation. As with all studies, there were of course limitations. Just a couple of main ones I wanted to highlight. Our terminology really had to work very hard. We were trying to bring quite a few concepts into one rateable description, which is something that could have been improved, if not solved, by having more questions or more rounds in the surveys. But participant fatigue is a real thing. And I'm sure the participants would agree that might have been a barrier to more of them being able to finish the process and end with us getting those results. The other one I wanted to just highlight is the load-bearing masonry wasn't really represented much in the strengthening type category. It's believed, so participants had the option to put forward further suggestions for adaptations that they thought were pertinent or had seen a lot. But actually maintenance and repair work was out of scope for this project, and it's felt that for masonry buildings, strengthening is often seen as coming under one of those two categories, and that might be why we didn't get any of those coming through. In terms of conclusions, this was quite quick, but we obviously discussed the financial barriers and that those are still governing adaptive building reuse at the moment in the UK. In terms of the physicalities of the buildings, the participants identified having a clear frame structure with a generous floor to ceiling height and a really clear structural grid as all factors that helped enable adaptive building reuse. Probably none of those are too surprising, but it's good to confirm it for this country. In terms of the structural adaptation options themselves, it seemed that the concrete frame buildings were at least viewed as being more challenging to implement our structural adaptation options. And then finally, of the 4 different categories of structural adaptation options, the strengthening type adaptations seem to have the lowest barriers or were least problematic. In terms of what happens now, I'm going to be, or have been, putting together a set of associated rules that I can put into the computational model, along with case studies for existing buildings and a set of aspirational building briefs. So then I can validate the computational model and continue to explore the suitability and flexibility. A challenge potentially for all of you would be to consider what we can do so that these concrete frame buildings could align more in terms of the perceived difficulty with the steel frame and load-bearing masonry, so that the adaptation is just at least the same level, if not as easy as those construction types. And finally, if even for new design, it's worth considering what might happen in the future. So either designing for deconstruction or making sure that the design information is clearly available for future engineers. Lastly, I'm just going to finish by a little plea for collaboration. If anyone has any particular insights on adaptive building reuse projects they've worked on or would like to share any case studies, please feel free to grab me in the break or ping me an email, which is here. Thank you for listening.
Okay, so our next speaker before we go to lunch is Dan Bomper. Dan is a chartered structural engineer and senior lecturer at the University of Surrey, specialising in sustainable and resilient structural engineering. He's published over 100 peer-reviewed papers on structural materials and engineering, and he leads research initiatives on net positive building systems, structural reuse, and decarbonisation in seismic design. He's also active in developing methodologies for evaluating disassembly capability and reuse potential of structural systems. And Dan is going to be presenting to us today on testing for structural reuse. Oops, sorry, jumping your slide on. Over to you, Dan.
Thank you very much. I'm mindful that I'm the only thing between lunch and you, so I'll try to be brief, hopefully interesting as well. Both of these things cannot happen at the same time. Thank you for the invitation. So I think this presentation ties very nicely with the previous one. We're not looking at the whole building, let's say reuse, but more on the component, which is always a problem child, particularly in concrete. Before going to the testing itself, I want to put a bit of a background. We are very much aware of the responsibility that we have as civil and structural engineers to minimize carbon resource depletion of materials. In the UK, let's say, industry is responsible for about 20 million tons of ready-mix concrete being poured every year. So there is a lot of carbon there, and about 176 million tons of aggregate. So there is a lot of depletion of natural resources. So of course we need to carry on building. We need concrete, but where we can, we try to minimize this if it's possible. We're also responsible for quite a lot of waste, and this is taken from the last DEFRA report. The construction demolition sector is responsible for about 61% of the total amount of waste, and about 33%, if I read correct the top of the diagram, it's mineral waste. Most of it is concrete. So we do have a responsibility here to try to curb these numbers and minimize them. You're probably aware there is a decision tree for design approaches in existing buildings. And as says, this is an adaptation of what it's in the circular economy statements by the London Mayor, which was published in 2022. And I think it's a requirement for any building built in between 125 or City of London to follow this. And then if we look at the right-hand side of the diagram, when we have the waste hierarchy rewritten for the built environment, we have at the top of the pyramid, which is adaptive reuse, probably retain and retrofit, what the previous speaker was mentioning, which of course is the best, because that will be associated with minimum use of new resources and minimum energy for demolition and so on and so forth. Then if we need to remove some part of the structure, we can do partial retention and refurbishment. And there are quite a few successful case studies in the last years, which I've been reading to the structural engineer. And then, of course, maybe some of the buildings are not fit for purpose and they really need to be removed from site. We can lower our expectations and go for disassemble and reuse. Now, we know in steel there is an SCIP 427 document. This is quite well qualified. For concrete, things are a bit more different and difficult. However, there are options to reuse on site, use on a site nearby or an off-site. The worst case thing will be to demolish and recycle. Recycling, it's still one of the end-of-life routes for concrete, the most common, but reusing that material comes with some addition of energy and other materials. At the bottom of the pyramid, not even included in this waste hierarchy, is disposal into landfill. So probably this is being completely removed because we should really not think about that all together. I was mentioning about end-of-life routes for concrete, and now I'm looking more of at the lower part of the pyramid. So the most common, it's right in the middle, is recycling and reusing road bases or infrastructure, which is downcycling and losing some of the value of the material. The other way would be to use it in new concrete. I'm part of the FIB Task Group 4.7. We've developed a FIB bulletin, which is going to be published next year. It's a very detailed bulletin, which gives all the work that has been done so far, will be very useful. When we use it in new concrete, it will come with addition of cement or super plasticizer. So if we look at carbon emissions exclusively, recycled concrete aggregate might not be sustainable. It might be exactly the same as new concrete. Of course, there is quite a lot of work in the last 10 years on recycling and recovery of the fines and use them as cement replacement. So that's really up and coming. So it's a very valuable research. And then the other side, which I'm going to focus more on, it's the secondary use of and structural use of elements cut from existing structures. And whilst in the UK there are not that many cases documented, or at least we are not aware of any, in Europe there has been quite a lot of work, and there is a very good paper which I always encourage anyone to read from EPFL for Celia Kupfer, who reviewed about 77 cases in Europe about structural use, documented from 65 until very recently, and they vary from single-story buildings to more than 4-story buildings, depending on the period. The best candidate for this kind of reuse cases would be like the LPS structures, large panel structures that we have in the UK. For example, we have a large building stock, which probably at the end of life, many of them will be knocked down at some point. So there is some benefit there. And then there are some successful stories in Netherlands for typical panelized structures, but also using a bridge, a composite bridge for various application in residential houses. So there are quite a lot of stories. Now I'm moving to the case study. I would say it's a case study with some research that I'm presenting. It is part of a wider project with industry. I'm going to acknowledge them towards the end. And we were contacted by some colleagues from Europe and 3XN if we can test something extracted from an existing building from central London. The project is Euston, which is planned for the demolition, I would say, or change of function. And then because of circularity driver sustainability, they would want to minimize the impact on the environment. As a decision was to keep the foundations, which seem to be sound, keep the core of the structure, and try to use as much as possible from the remaining structures, like the floors, the columns, in a way or another, but after being removed. And instead of the current structure, there will be a steel frame building with a lot of concrete in it. What we were tasked to, of course, whatever is not being reused at the higher scale of the waste hierarchy would be recycled and used as recycled aggregates in some applications. So what we're tasked to if we are able to test a concrete plank extracting from a ribbed slab, this was extracted from the first floor of the building, and then this would supposedly be used in a steel frame building, where it seems that these two materials or components do marry the best together. So we would use this plank as a replacement of a hollow core plank with minimum carbon. This is what we received. We're told that the slab would be about 4.5 meters long, 1.5 meters wide. It will have between 2.5 and 3 tons, which is quite useful. We also got this cross section, which told us that it has a geometry. There are 2 ribs, reinforcement, 216 or 20 millimeter bars, perhaps some links and some mesh. So there have been some site investigations, but there were so many unknowns, we don't know. The slab was removed by the contractor. It took technically about 5-6 hours altogether, but it was the first time this kind of technology has been applied, at least in the UK. So they had to do a bit of a trial and error. So they spent a day for the propping, then a day for setting out and preparing the cut. The cut itself was about, with the setting up the equipment, moving the blades and so on and so forth, was about 3 hours, but the effective cut time was about 15 minutes from what I understand. They took a day off. It was too tiring already. And they came back after a day and they removed it in about 1 hour and 15. This was in March last year. We received the slab a couple of months afterwards. This is the back, let's say the back road at the University of Surrey, entering the lab. When we got the slab, what we saw initially on the brief, it were 2 reinforcement bars, quite small. When you can see on the right-hand side, there are a bit more, a bit heavier than we expected, and I'm going to get to that in a minute. So what we've done at Surrey, we've done some preliminary studies. Before we put this into the rig, we need to make sure that we kind of expect what kind of failure is going to have and what is the capacity, just to make sure that we can hopefully fail the slab. I've done some stiffness and strength calculations, some basic section analysis, some linear modeling, just to understand if there are any deformations in the rig or elsewhere. Then we've done some internal external geometry assessments, basic caliper measurements with a tape measurer. We've done also some photogrammetry, which we're going to use in the future for other work. And we've done also some GPR assessments to understand the reinforcement layout. Then we went into some material tests. We did have a bit of a feel of the concrete strengths in the slab. So when we got the brief, we were told that the strength will be between 40 and 90 megapascals, which was a good information. At least we knew that is not low strength. And then we've done some destructive tests on the series bars, and we've done finally 3 tests actually on the slab itself. One full span stiffness test, similar to the conditions that the slab would be on site, supported at the edges. And then we've done 2 half span tests to look at the failure mode. So this is more of like, if you look at social media, there is Instagram versus reality. So the left-hand side, it's more Instagram, and then we come to reality. So we were told, this is what we had in the brief, and this is the information that we had until the slab arrived. A reinforcement ratio about 2.4. We prepared, it's going to be probably a shear failure, no shear links. It's going to be we would quite expect failure mode. Now, when we received the slab, there were these quite large twisted bars, which were used in concrete buildings in the 60s. I think it's a 49 standard that gives guidance on this. And then the reinforcement ratio of this slab, it's about 9.7%. So it's a very heavily reinforced. It's more like a steel concrete reinforced structure than a typical ductile structure that we have. So the capacity that we were prepared for to test, it was in the end 4 times, or at least altogether. So that was just before the start. We've done this analysis just to understand a bit of behavior, nothing very specific. It's just confirmed the hand calculations that this is going to be quite a stiff and a strong slab. The GPR measurements indicated what we also saw from the cut faces of the slab. So because this was directly cut on all sides, we could see the ends of the reinforcement, and it's just confirmed. But I think it's very important to have a secondary second view, and this was done by TraceSI, which is one of our colleagues there. We've done a bit of a 3D model. This is photogrammetry, so we are going to use this for further analysis. We want to do a bit more nonlinear analysis to do some parametric studies, to look at various concrete strengths, reinforcement ratios. It should be very useful to understand which are the ranges of behavior of these kind of systems. In terms of material properties, the non-destructive tests, particularly the rebound hammer test told us that it's about 50 megapascals. UPV was not very good. It's probably because which is at the bottom slide, is because of the position of the slab and the difficulty of accessing. So it's quite a large variation. So we went with the one on the top, which is closer to what was obtained from coring on site. We extract after the test the reinforcement bar. This is how it looks. The 35 millimeter twisted bar. Of course, we had to fail the slab first and then remove the reinforcement. We didn't remove and then test the slab. It would have been much easier for us probably. Then we extracted, because it's very difficult to test anything which is of this size in any machine. We had to do some coupons, extract some coupons. The reinforcement characteristics were very much similar to what they appear in the standard that was giving qualification characteristics for the rebar. Now we moved on to the full-scale tests. So we've done 3 tests, 4-point bending test in which the slab was supported at 2 ends with the load applied by 2 points, as you can see there. But this is very close to what the slab would look in practice. And then we've done 2 half-span tests on two of these tests. We loaded the slab up to around 240 kilonewtons. So when we stopped for various reasons, we took some measurements of the crack. But when we removed the load, the slab was in really perfect condition. All the cracks closed altogether. So it was a very stiff. And this is very useful only to get the stiffness of the slab rather than anything else. We've done the 2 tests on half of the spans, and what you see on the diagram on the left, there are 2 low displacement curves, and it shows us that one shows the displacement of one of the ribs, and the other side of the ribs, it just tells us that the black curve, that there is a bedding in effect, and this just tells us that the bottom side of the slab was not perfectly smooth. So when we prepare specimens in the lab, we have perfect formworks, everything looks good. We have put them perfectly on the position. When we take things from site, the cast surfaces are not perfect. So then we had to put some shims and supports, but then it was still a bit different. And then this is the failure mode. I have a small video. Hopefully it starts gradually. You would see right in the middle a diagonal crack. So the support is on the left-hand side and the load application point on the right-hand side at the top. The crack opens quite smoothly. So the initiation of the crack was around 450 kilonewtons. The capacity was 550, just 10% below the machine capacity. And then what you can see here as well, there is a longitudinal crack, which was a post-debonding, I would say, because when the slab was cut, there was no additional anchorage, nothing else. So the only bond was between the rebar and the concrete itself. Now, moving very briefly into results, I think I'm very well in time. So what you see on the dashed, so this is the intended purpose of the plank of the reuse slab is for an office building. And what you see in dashed orange curve or red, it's what is the design demand. What you can see with the continuous black curve, it's what we loaded in the first stiffness test. And then what you see with the red cross, it's what is the capacity of the slab. So there is quite a lot of reserve capacity, and I'm using this example from Macon, which is also a nice structural design for net zero. If this is what we need for a design for an office building, this is what we got in terms of capacity. So this is going to be quite a crowded office party if people would fit in. It just tells us that these concrete structures have been built well, probably, and they are robust and strong enough. Even if we just cut them and we forgot about the anchorage, we don't have any sort of anchorage length except for the direct bond. They are still quite fit for purpose. So what we've done at SERI, we've done some perimeter studies, some internal external geometry assessments. We've done some material properties that we do and the structural tests. And this is wider of a larger structural use for workflow. I don't think we have yet a clear workflow on how to deal with these studies. So I think this could be a beginning, I would say. Of course, there need to be quite a lot of feasibility studies, field investigations, GPR, coring, non-destructive testing, selective deconstruction that's done by the contractors, then some focus tests in the lab to understand the actual behavior to failure and put strain gauges, deformations, and then going back to the site, do some upgrading reinforcement if we need to, whether with steel, maybe with FRP, with whatever we need to. We do some order assessing, and we would probably need to do some selective proof testing just to make sure that if we cut 100 of these planks from the existing building, we probably need to test at least 10 for reliability purposes up to the service limit state to see if they behave in the way that we expect. In the wider context of circularity, we should also have material passports to everything that we are using, so we can trace them throughout their lifetime, both in terms of carbon, structural characteristics, and so on and so forth. And this takes me to the main takeaway. So we've demonstrated that a slab or an element extracted from a building from central London, which is Euston, can be used as a plank in a new structure. We proposed and we through this case study showed a complete laboratory workflow which can be used for structural reuse. I'm not going to go into the capacity, but it just shows that this is possible. So the team came with these solutions for the reuse of the planks. Of course, we need to provide some tying capacity for this. So probably with the addition of couplers and some other angle connections, this could be sorted out. All these results are available. So this is the whole team. So acknowledgements to British Land, Trixen, Arup, JF Hunt, and Theobald, and my colleagues at SERI. All the reports are available online. So if you access them through this QR code, you can download them, including our test report. And if you have any questions, please do always get in touch. Here's a QR code. So that's it, I guess. Thank you very much. Just one final point. So in terms of, because we started from the carbon emission side of things I didn't mention. So the carbon associated with the reinforced concrete plank that will be used in a steel frame building will be about 300 kilograms CO2 emissions per plank. For this particular slab will be 130 which is 1/3, and this account for the transportation to Surrey and return to demolitions to whatever to the yard. And probably this doesn't account for the idle time on M25, which would have added a bit more carbon. But if it's used inside, probably this will be maybe 20%. So there are some benefits there.